So at this point, we've used our favorite method of all time, completing the square, to solve a generic version of our favorite type of equation, quadratic equations. So if I have any equation of the form ax squared plus bx plus c equals 0, for example, maybe 3x squared minus 17x plus 41 equals 0, then all I need to do is plug in a, b, and c into this equation, and I'll get my two solutions, or roots, for x. Now I'm going to do some examples of this shortly, but first I just want to observe some simple things about this equation. First off, a lot of the computation is this b squared minus 4ac stuff. So let's give this a name. So I'm going to let capital D denote this, and we're going to call this the discriminant. So D is b squared minus 4ac, and this is the discriminant. Now, why is this called the discriminant? Because it discriminates in a good way between three different cases. So when d is less than 0, we have the square root of a negative number, because this thing under the square root will be less than 0, or negative. Whenever we have the square root of a negative number, we'll get imaginary things here. So we'll have two complex roots. What about when d equals 0? Well, then we'll just have the square root of 0 here. And we'll be adding and subtracting the square root of 0, which is just 0. When you add and subtract 0, either way you're going to get 0, so you're not going to do anything. So in this case, we'll have the same root twice. So we'll have a single repeated root. We say that it's a root of multiplicity 2, because it appears twice when you solve the quadratic equation, both when you take the plus case and the minus case. And if d is greater than 0, well, here there's no funny business. We're just taking the square root of a positive number here, and so we'll get two distinct real roots. All right. Now in in any of these three cases, we can get x, assuming we already computed d, as x equals negative b plus or minus square root d over 2a. All right, because if we let this be d, then this equation is the same as that equation. So I like to call this the two-step quadratic formula. So in the two-step quadratic formula, we first compute the discriminant d, which tells us which of these three cases we're in, and then we find x using that discriminant. Next up, some examples. Okay, let's do some examples where I use our two-step quadratic formula, which I wrote down here, to solve some specific quadratic equations. First up, we want to solve 5x squared plus 3x minus 4 equals 0. So the first step in applying the quadratic formula is identifying a, b, and c. So our general form is ax squared plus bx plus c equals 0. So a is the coefficient of x squared, which is 5, b is 3, and c is negative 4. Next step, compute the discriminant. So capital D, the discriminant, is b squared minus 4ac. So b is 3, so that's 3 squared minus 4 times 5, that's a, times negative 4, which is c. So 3 squared is 9. Negative 4 times 5 is negative 20. If you multiply by negative 4 again, you get positive 80. So 9 plus 80 is 89. Okay, so this is greater than 0. Whenever our discriminant is greater than 0, we have two distinct real roots. And what are they? Well, they're just given by the second part. So the roots are x is negative b. In this case, b is 3, so that's negative 3, plus or minus the square root of d, which we just computed, was 89, all over 2 times a. So a is 5, 2 times a is 10. And that's it. So if 89 had any perfect square factors, we would extract them and simplify the square root. But as it happens, 89 is a prime number, so there are no non-trivial factors. So this is our final answer. And these are the two distinct real roots that we mentioned earlier. Let's do another example of using the quadratic formula to solve a quadratic equation. So let's suppose we want to solve x squared plus 2x plus 1 equals 0. First, we need to identify a, b, and c. Well, note that we are in the descending power of x order, our standard order, namely ax squared plus bx plus c is 0. So it's easy enough to see that c is 1, b is 2, and what's a? Is it 0? Because there's nothing here. Well, no. There's an invisible times 1 there. Because x squared is the same as 1x squared. So a is 1 in this case, not 0. Okay, next up, we use the first equation in our two-step quadratic formula. So our discriminant, capital D, is b squared minus 4ac. So b squared, okay, so b is 2, so that's 2 squared minus 4 times a, which is 1, times c, which is also 1. So this is, well, 2 squared is 4. 4 times 1 times 1 is 4. So 4 minus 4 is 0. Okay, so remember what happens when the discriminant d equals 0? That means there's a repeated real root. And I'll show you what I mean by this. It comes from the second equation. So x is negative b plus or minus square root of d over 2 times a. So negative b is negative 2. D is 0, so plus or minus square root of 0. And 2 times a is 2 times 1, which is 2. Well, the square root of 0 is just 0. So we get negative 2 plus or minus 0 over 2. So usually when we do this plus or minus thing, we have two different answers. But here, it doesn't matter whether you add 0 or subtract 0. It's the same thing. Either way, you just get negative 2 upstairs. So this reduces to negative 2 over 2, which is negative 1. And sometimes teachers like students to write negative 1 comma negative 1, just to emphasize that this is a repeated real root, but it's up to the teacher what they prefer. Observe, too, that we could also see that this is a repeated real root by factoring the original equation. So if we factor to x squared plus 2x plus 1 equals 0, well then it factors as x plus 1 times x plus 1 equals 0. And if we set each of those factors equal to 0, we get x plus 1 equals 0 for both of them. So for both of them, the solution is negative 1. Let's solve yet another quadratic equation using the quadratic formula. So here we have 6 plus x plus 3x squared equals 0. Now the first step in using the quadratic formula is identifying a, b, and c. But we need to write this in the standard order in terms of descending powers of x. And this is not. This is sort of an attempt to trick us. Okay? So we need to rearrange this in standard order. So we would have 3x squared plus x plus 6 equals 0. We move this one out front and this one behind. So here it's clear that a is 3, b is 1, because remember there's an invisible 1 here, since x is the same as 1 times x, and c is positive 6. Now, had we not rearranged this, we would have thought a was 6 and c was 3. That would have been wrong. Anyway, next step, the discriminant. So d is b squared minus 4 times a times c. So b squared is 1 squared minus 4 times 3 times 6. Okay, 1 squared is 1 times 1, which is 1. 4 times 3 is 12. So we would have 12 times 6 is 72. So we have 1 minus 72 is negative 71. Now negative 71 is less than 0. So when our discriminant is less than 0, it tells us that we have two complex roots. Let me write that here. So something involving I somewhere. And what are these two roots? Well, we go to the second equation. So x is negative b, so negative 1, plus or minus square root of d, so d was negative 71, all over 2 times a, so 2 times 3. Okay? So what's the square root of negative 71? Well, 71 is negative 1 times positive 71. So it's the square root of negative 1 times the square root of 71. And then what's 2 times 3? That's 6. Okay, so we're almost done. Just remember, square root of negative 1 we call I for our imaginary root. So our final answer is negative 1 plus or minus I root 71 all over 6. You see that we do indeed have two different complex roots.